Dear friends, again I have come up with another proof of Pythagoras theorem. This is again I have named as Acharya's method number 5. As usual, for further discussion, my contact email address is there, so you are free to contact and post your points. And I hope you like this proof as well. And this approach is again unique, and this time the approach is based on analytical reasoning and by numerical methods. And you will find that finally there are no big equations, and through analytical reasoning and certain observations from geometry and certain values, one can conclude that c square equal to a square plus b square we can finally arrive at. So let's see how we approach analytically and the reasoning behind it. So let us think of a function of c. Function of c will try to guess from analytical reasoning, because as usual that area of triangle ABC is AB by 2, so there is no c, so c must be a function of a and b, c must be related to a and b. And when you are trying to frame the function, before that we make some observations, like when a equal to 0, c equal to b, when b equal to 0, c equal to a. This is sufficient to imagine that the c is a function of a and b in a summation fashion, and not by multiplicative or divisional way, because if that is the case, when we put the values of a and b, c becomes either 0 or undefined. So we frame the equation like this: c equal to k a to the power n plus l b to the power n. N is the power, k and l are constants, and c is the length of the hypotenuse we are interested about. So if this is the general function, it should satisfy the values known, like a equal to 0, c equal to b. If this is the case, we find that b equal to l into b to the power n. So this condition can only be satisfied when l equal to 1 and the power n, it must be either 1 or we keep it as n for the discussion later. So let's see what happens when we take that n equal to 1. For that we move on to the second slide. So we find that when we take n equal to 1 and the previous equation is satisfied for l equal to 1, we find that since a and b are interchangeable, we find a relation like c equal to a plus b as the governing function. But in such a case, formation of triangle is not possible, as to form a triangle, c should be less than a plus b. So n equal to 1 is not a feasible power of either a or b. So we move on, saying that my function should look like c to the power n equal to a to the power n plus b to the power n, and k and l already we proved that they must be 0 each. And a question may arise, why the power of a and b, they must be equal and same, because as we know, A and B, they are interchangeable. So in the geometry, A and B, they can change their position, but still the condition of C should be satisfied. So power of A and B must be the same. So C to the power n equal to A to the power n plus B to the power n, the power of C as n, it again comes back from the previous equation number 1, where the basic equation was framed like that. So after being very sure of the general equation like as given in equation number 2, we move on to see what happens when A equal to B. That's why on the left I have drawn a new right angle triangle with sides A, and I have created one midpoint of hypotenuse at O. And when I compare two triangles created by this way, that is triangle ABO and OBC, we find these triangles as similar in terms of all sides and corresponding angles, and how angle BAO turns out to be 45 degrees, and in such a case the hypotenuse C becomes A root 2. This is a typical example for a right angle triangle with sides when sides are equal and of the length A. So when you talk about Pythagoras theorem, it must be a general theorem for any length of the side. So that's how we move on to the third slide, where we'll apply the numerical method for different values of n equal to 0, 1, 2, 3 and any other positive integer, and whether it is satisfied. We find that when n equal to 0, the relation is not valid. When n equal to 1, we get a conclusion C equal to A plus B. Already we have proved that triangle formation is not possible. When we put as n equal to 3, we find that when A equal to B, C takes a value of 2 to the power 1 by 3 or cube root of 2 into A. But in the earlier, we have already proved that when A equal to B, C equal to root 2A. So n cannot be 3. When we go for other values of positive integers n greater than 3 like 4, 5, 6, we find that the value of C for A equal to B will turn out to be 2 to the power 1 by n into A, and they will never become root 2A. Only when n equal to 2, we find that C square equal to 2A square or C equal to A root 2, and it is exactly matching what we found out from the earlier geometry when A equal to B. So finally, through this numerical method as well as the analytical method explained in slide 1, we can conclude that the relation is only valid and satisfied the results found from other geometry is C square equal to A square plus B square. Only for n equal to 2, this satisfied the results found anywhere. That's how we prove the Pythagorean theorem must be of the form C square equal to A square plus B square. Thank you very much. Hope you liked it. This is a very unique approach, and please like it, subscribe my channel, and thank you very much for watching. Good night.